So now let's go in today's normal lecture on energy-based models. So I'm going to give a brief overview or intro on what is an energy-based model, although we discussed a bit in the first lecture, so I'm not going to spend too much time. Then we're going to spend most of our time on Boltzmann machines and restricted Boltzmann machines, and discuss briefly on deep Boltzmann machines, deep belief networks, and deep Boltzmann machines. Now, these were early energy-based models. In the next lecture, we're going to see also score-based and diffusion models, which are basically advanced variants of these early models. Now, energy-based models for distributions are having a great advantage that they are also very flexible in the types of shapes, the types of distributions that they can capture. If you have, again, a prescribed probability distribution, like a Gaussian, Bernoulli, whatever, what have you, this is very inflexible. It's just like a very simple, because it's a formula-based way of determining or defining a distribution, you can do only so much. However, we can capture much more complex densities by having an energy-based definition, where we have a function f in the denominator, and we can simply convert this into a probability density function by normalizing it with a constant z, where z is just an integrated version of the denominator. So you take the function, you integrate it out over all your inputs or all your possible inputs, and then this function is guaranteed to look like a probability density function. Do you remember this? So this is even more comfortable specifically for optimization in our setting if our function is combined with an exponential. So we take the exponential of our function over z. The reason is that the exponential, well, a lot of the distributions already have an exponential form, like the Gaussian, right? It's exponential of minus 1 over 2x minus other blah. But also the exponential is very nice for optimization because it will pass it through the logarithm, so for the log likelihood, so that we can convert products into sums. And then the logarithm and the exponential cancels out, and then you remain with just the function. So in terms of optimization, an exponential in your denominator is very practical. You can see this form also in terms of an energy function. So your exponential of your f theta can also be, you can see it in papers as the exponential of your minus energy. It doesn't change anything in practice, that's just a way of writing it down, a different way of writing it down. Clear?
These are also the integral over the exponential of x.
Sorry?
Is z now changed as well? That is the
Yeah.
integral of the exponential?
Here f, I mean that's how you say it, but f here is like the whole thing here, or since the exponential is just a standard function, you can just say f is instead. But either way, the z remains. So let's say f can be any function, right? Like it can, so right, x, this is f, and this is y. Y is f of x, correct? Let's say that this is always positive, so this is a requirement to have a valid probability, right? Like they have to be positive. This is not necessarily probability yet, is it? Because this can, like y can be like, let's say 10,000. And if you take like the integral of fx dx, so the area here under the curve, so the area under the curve, which which is your f of x dx, is not necessarily 1. However, for probability, to have probability, a valid probability, you have that px dx must sum up to 1, right? Like all your probability outcomes cannot be more than 100%. So how can we make this easily a valid probability such that this is always equal to 1? You just divide here. Sorry. You just divide f of x with its integral, and then this whole function will be guaranteed to be 1. You just normalize the function. Clear? Now, if your function f is f or exponential of f or tan h of f or whatever, it doesn't matter. By just, well, tan h shouldn't because it's negative, but like x squared or whatever, then it doesn't matter. Like, for as long as that you're integrating that combination of functions, that gives you a valid probability in the end. Of course, the question here is, sure, like f can be anything. It can be very complex. It can be very weird. How do you do things with it? How do you evaluate it? So if I give an x, is it to compute probability? Can I sample from it? Can I do things that I would like to do with probabilities? Also something to remember here. So in energy, here the energy formulation is usually, or let's say, closely associated with physics. And in physics, you've got the concept of energy, and specifically a system that has lower energy is a desired system. You start from like very high entropy, and then you want to reduce it, and then this means lower energy. So high probability means lower energy. Okay, you had a question?
And what means comfortable here? Like if we squeeze the, is that just
Squeezing, like we just put the exponential here. It's more comfortable because as I said, like the most obvious, in practice, it means that it's very easy to combine it with logarithms in the log likelihood computation.
Okay.
If you wouldn't have that, then you would have to compute explicitly logarithms.
Yeah.
And logarithms are, well, it's better if you don't have them in the end, right? Like it's good if you have them in the theoretical model, in the mathematical model, and it's even better if you can avoid computing them in practice, because, well, logarithms are like this, right? Like they're very steep and everything, so. So energy-based models for distributions have a great advantage that they bring us great flexibility in defining our energy function in our distribution. Sorry. So we have great flexibility in our model design because we can literally pick whatever we want. The only real requirement is that our function, well, it's not even that. Like this is already positive with the exponential. So the only real requirement is that our numerator is positive. With the exponential definition, like that's another reason why it's comfortable. Gives us that by default, like the exponential of any function is positive, right? So we can really just be crazy. You can put whatever you want here in f, it works. So if our final objective is to find the best possible distribution, to have any possible shape, then an energy-based model can do that. So any distribution can be learned. However, this comes at the cost. As usual, as we said before, time and again, with generative models you have intractabilities because normally you're going to have an integral somewhere. So you either have to somehow make it easy to compute, or you have to approximate it, or you have to compute it, you have to sample from it, whatever. Like there must be a way to go like to address this problem. And here the intractability, the integral comes in the normalizing constant, or otherwise called partition function. It's a normalizing. It's called normalization constant but be a bit careful with the term constant here. Constant is only after training. During training, it's not really constant because it changes with as the parameters data change. So it's constant within like one step, update step, but over the course of the training, the partition function changes it as well, which means that has to be part of your gradient. It's not a constant and therefore it's cancelled out in the gradient computations because it's constant. No, it's not a constant like that. Okay. Now, because the normalizing constant is an integral, and if you have a very weird function, then you can have a very weird integral, right? That's just intuitive. So which means that something can be hard. So you can have a general method for something, like using cumulative distribution functions. However, this will add one more integral in your process. So CDF approach, you can sample generally, because you already have particular constraints. However, you have to compute another integral, and that doesn't make things simpler, it makes things harder. Evaluating will be hard, or can be hard, during training, because you have to compute the integral in principle. And at least in the vanilla version, we don't have latent variables here. So this is just your probability density function, and that's it. So you cannot do really representation learning. With are the basics of energy-based models? Okay, this is very basics, like the very basics. A very important trick that is used time and again with energy-based models, and that's important to, like, again, if anything, remember from this lecture, is that the ratio of likelihoods does not have, like, the ratio of likelihood removes the partition function problem, the normalization constant problem. What do I mean by that? At a single point, it will be hard to evaluate an energy-based model because you have to compute the integral. However, if you have 2 points, xa and xb, their relative ratio of likelihoods is much simpler to compute because the normalizing constant cancels out and you're only left out with the nominators. And the nominators are easy to compute. It's just our functions or our energies. So you have no normalizing constant anymore. So if you can define ways during training, during sampling, during evaluation, such that you can use ratio of likelihoods to find good parameters, to sample new points, to make comparisons, that makes things easier. Is it clear? Any questions? So ratio of likelihoods, you will see it all over the place in general with convex distributions, from MCMC sampling to energy-based models. So what happens? Because it alleviates the requirement for having a normalizing constant computed. And some examples of energy-based models. So you've got the Ising model. Have you done the Ising model in the machine learning one? No. Well, that's the simplest of all. So you just have unitary terms, which basically tells you how much energy each state has, each pixel dimension has, as well as a binary term, binary or dyadic, like pairwise term, which tells you basically what is the energy of two, let's say, pixel, the neighboring pixels to be very similar. So let's say this is your image. Your observed variables are your pixels, x1, x2, x3, x4, etc. And let's say that these observed variables are noised up. So you have like salt and pepper noise, and you want to make, if we want to find the clean version of the image, which you call y. So a reasonable assumption is to say that, well, in general, my pixels will not change too much from what I already see. However, I want to make sure that neighboring pixels have similar values, right? Like if I have a very sudden white pixel around black pixels, this doesn't sound very likely, so I should penalize this here. So basically, this is what the Ising model does. And it's an energy-based model because we define again a function. So a function here is simply computing. We say our energy function is simply computing a energy for each dimension independently, and adding pairwise energy terms per dimension, per pair of dimensions. That's the Ising model. Whatever, like, it doesn't really matter, it's already part of the course, I'm just explaining the Ising model very quickly. Other energy models is, for instance, product of experts. So if I have like three models, neural networks, probabilistic neural networks, I don't trust one of them optimally, like best. I just say I want to have somehow them combined. How are you going to combine them such that you still have a probability density function then that you can optimize? Well, one way of doing that is just combining them in an energy-based model formulation. You multiply them, and you're dividing over their normalizing constant. And restricted deep Boltzmann machines is like what we're going to see, a bit more advanced, or at least more sophisticated. Okay, I think we have to have a, let's say, a 5-minute break, or 10-minute break, and we continue at 10 past 10.
On Canvas in the when and where page, there are office hours for some modules, but there isn't a room. Do you know where that is?
I think the respective like teachers' room.
So where is that?
Oh, we don't. Okay, I'll ask.